In this problem, a given 18-inch reinforced concrete sewer with a Manning N of 0.013 is being installed to transport stormwater away from a detention basin. For every 100 feet of length, the vertical change will be 0.5 feet. If the sewer is required to achieve a minimum velocity of 2 feet per second to prevent sedimentation, what should the depth in this sewer be? So this problem provides us with an opportunity to solve something called partial flows. We can do this in about 4 steps below. First, we have enough information to use Manning's equation to calculate the velocity in the sewer when the sewer is flowing full. Manning's equation can be found in section 6.4.5.1 if you need to see it. This is going to be equal to V equals 1.486 over the Manning N times the hydraulic radius to the 2/3 times slope to the 1/2. Hydraulic radius, as you may recall, is the area over the wetted perimeter. We can solve for area and wetted perimeter and then plug this back into the hydraulic radius. So the equation for area is going to be pi times d diameter squared over 4. In our problem, that's going to be pi times 1.5 feet from the 18 inches here, squared over 4. And our area is going to solve out to 1.77 square feet. The wetted perimeter is going to be equal to 2 times pi times the radius, otherwise known as the diameter over 2. So in this, it's going to be 2 times pi times 1.5 feet over 2. And this is going to solve out to about 4.71 feet. Putting 1.77 over 4.71 solves out to about 0.375 feet, which is our hydraulic radius. The slope value, we can see from the problem, says for every 100 feet of length, the vertical change will be 0.5 feet. So following our convention of rise over run, we will do 0.5 vertical feet over 100 feet. And this will give us 0.005. And this will be our slope value. So plugging all of these terms into Manning's equation, we can see that 1.486 over 0.013 from up here times 0.375 feet to the 2/3 times 0.005 square root. And this will calculate out to just about 4.2 feet per second when the pipe is flowing full. So step 2 is going to be finding the ratio of the minimum desired velocity to the full pipe velocity. And this is really easy. We're just going to plug in our minimum velocity of 2 feet per second over 4.2 feet per second and get a ratio of 0.48. Now, step 3 involves going to the plot in section 6.4.5.3 to find the hydraulic element plot or the partial flow plot. I will include a screenshot here. Tracing up on the x-axis from 0.48, which we calculated in step 2, we can stop at the solid line for velocity. This is because in partially filled sewer pipes, the end value can often vary with the flow depth. Next, we can trace to the left x-axis, and we can find our ratio of flow depth to diameter. And this value is just about 0.2. Now, all we have to do for step 4 is to apply this ratio to our current pipe size. So we have 0.2 times 1.5 feet, and converting back to 12 inches per foot. Forgot to note here that depth is in inches. And this will solve out to about 3.6 inches, which is our first answer over here. Some quick notes. Due to the nature of partially filled pipes, we can't apply our ratio calculated for the velocity directly to the depth. Nor can we plug in the velocity of 2 and back calculate for depth, since we wouldn't know the geometry of the partially full pipe. This is why we are using the partial flow diagram to solve this problem. So if you're comfortable with Manning's equation, and you remember that this plot exists on the exam, you'll be in great shape if you come across a question where you are asked to find a given velocity or flow at a given depth within a sewer. And that's it.